Okay, so unfortunately for those of you who are watching just the recording and couldn't join us, you just missed our philosophy appetizer and some announcements about the exam. But maybe what I'll do is I'll redo the announcements later in our optional session. That way you'll have it in that recording. If you guys can remind me of that later, that'd be great. Okay. All right. So we have pretty much almost wrapped up our study of acids and bases, which has taken quite a while. We've studied many aspects of it. And tonight in our optional lab session at 7, if you guys want to join to work on that assignment together, which is due tonight, but you don't have to do it with us. You can do it by yourself. We are going to be wrapping up our study of acids and bases and buffers, and the study of the equilibrium constant of weak acid ionizations, the Ka. All right. But today we are going to switch over to a new topic. It's still Unit 16. This is equilibria in aqueous solution, but we are going to be looking at a different kind of equilibrium. So let's go to our PowerPoint presentation here. All right, here we go. And let me make sure I got this. Okay. All right, here we go. So let me see if I can kind of like spike a little bit of your memory here. Back in Chem 1A, you remember this? You take two solutions and you combine them and bloop, you get some kind of blob in there forming, right? Remember that? Yes, we call them precipitation reactions. Now you should remember because we did a few of those with our qualitative analysis experiments. Speaking of which, there's a couple more still to be done, but they're going to be coming in after next week, right? So the other thing that you might remember is using one of these solubility charts or solubility rules. Remember that? Is where you look at different types of ionic compounds, and depending on which cations or which anions are present, you can look at whether they're soluble or insoluble, and then look at the exceptions there on the right side. Maybe the type of table that you use was like this one, more like a grid, like Battleship, where you can ask, for example, let's say silver. If I combine silver with, let's say, iodide, what do I get? So you go down the line here and you find that it is insoluble. So that is another type of these things. Now, by now you realize that everything that we're studying here is about equilibrium. So that means that even in a mixture where you have an insoluble compound, it's not all or none the way we've treated it in the past. Most of the experiments that we've done have to do with producing a precipitate, right? Which means that we are basically beyond the equilibrium state. But actually, if we were to look, for example, at silver chloride, remember this is one of our group 1 ions, and we said that we distinguish them because they can precipitate as chlorides. Actually, in the solution, what you have is an equilibrium between the undissolved solid and a small portion of the ions that are actually dissolved in solution. You can see them there on the right side. Now, this is an equilibrium expression. So there is an equilibrium constant for it. And that equilibrium constant is going to be called the solubility product constant. And we abbreviate it as KSP. And again, remember that in an equilibrium where you have solids or liquids, those species are not included in the equilibrium constant expression. So here we only include the dissolved ions, all right? So just that we can practice a little bit here, right? So let's say we have this one here, magnesium fluoride, okay? So what would be the expression of KSP for that? Let's give you a few seconds to think about it. Careful with the stoichiometry, right? Because in this case, there are 2 units of the fluoride ion. So that means that the expression is, yes, magnesium times fluoride squared. Don't forget that, okay? Be careful with stoichiometry here. Okay, let's try this one here. What would be the KSP expression for this one? Right? So that would be silver squared, right? Times carbonate. Very good. Okay, let's last one more. Okay, calcium phosphate, which would produce 3 ions of calcium and 2 ions of phosphate for every unit of the compound that actually dissolves in water. Yep, that's right. We got some major exponents in here. So it'd be calcium cubed and, oops, sorry. And phosphate squared, right? Okay, so hopefully you remember how these equilibrium expressions. Just want to make sure that you remember to take into account the stoichiometric coefficients as exponents in the expression of the equilibrium constant, which in this case we're going to call it KSP. So here is a table, not exactly the one you have in your top hat text, but very similar, where it lists different compounds and their respective KSPs. Take a quick look at these constants and their values, and what do you notice about their dimensions of those values? They're all very small, aren't they? I mean, look at the one for copper 2 sulfide. Gosh, it's like 10 to the negative 36. Same for the lead 2 sulfide. Although actually those guys are not very stable in solution. They actually decompose further. But you can see that all of these are very small, which means essentially that the typical so-called insoluble ionic compound yields a very, very small number of ions in solution when it's in equilibrium, all right? Now, many times when we either make the mixture, or for example, when we combine two solutions that might result in a product that is insoluble, we might not be at what we would call equilibrium concentrations, right? So what happens if we are not in equilibrium situation here? Well, let's say that I dissolve, let's say, silver chloride. Let's say I have a chemical reaction that produces silver chloride, all right? But remember, in this case, I don't know that we are in equilibrium or not. I'm simply producing this compound. I know that it's going to dissociate into the component ions, whatever little proportion, whatever little percentage of units are going to dissolve. So we're going to do the same thing we did with equilibrium when we defined what we call the reaction quotient. And this time we're going to call it the ion product. I'm going to call it Q. And essentially what we're going to say is that this is the product of the concentrations of dissolved ions under the given conditions. Let's say we call them, I don't know, let's call them, I don't know, we can call them the initial conditions, right? Maybe let's call them initial. So just like we did when we were studying the reaction quotient in equilibrium situations, this value of Q could be different from KSP. In other words, it's the same formula, but these are not necessarily the equilibrium concentrations. So let's say that we calculate this ion product and it turns out that it's smaller than KSP. Well, that means essentially that you are not getting the same value that you would get if the system were at equilibrium. And so what you have here is an unsaturated solution. In other words, this is a solution where the whole silver chloride would be dissolved, right? In other words, no precipitate is going to be formed in this case. What if the value of the ion product is the same as KSP? Well, that means that you are exactly at the molarities of these ions that give you equilibrium. In other words, what we call a saturated solution. That is a solution that has the maximum concentrations of ions that it can tolerate, right? Now, notice that essentially a solution that is in equilibrium between the undissolved solid and the dissolved ions, if you look not at the whole mixture, but just the solution itself, in other words, the homogeneous part that is the liquid solvent with, or water with the ions, we would say that solution is saturated. That's the maximum amount of ions that can be in there. And if we calculate the ion product and it comes up larger than KSP, well, that means that the right side of that equation is overloaded. And, Le Chatelier indicates, well, this is kind of super saturated, quote unquote, which means that you are going to get a precipitate in this case. So what this does is it allows us to do some calculations here. Now, just like with other parameters that we study, there are tables that give us values. Now, one of the interesting things is that for solubility, many times if you look in Wikipedia or any kind of other database, what you find sometimes is they don't give you the actual KSP value. What they give you is something called the molar solubility. In other words, the moles of solute per liter in a saturated solution. Or sometimes they give you simply the solubility, which would be the grams of solute dissolved in 1 liter of a saturated solution. I'll go one more than that. Sometimes the way they give you this kind of stuff is actually what they give you is the grams. Oops. What happened here? What happened to my pen? Grams in 100 milliliters. Gosh, I can't get this thing to work today. One of those days. Okay, just forget it. Okay, grams per 100 milliliters. Forget it. Let me erase this. All right. So what happens therefore is we have to learn how to convert between, let's say, the data they gave us, which would be the molar solubility or the solubility, and KSP, so we can do problem solving, of the chemical equilibrium kind. So let's say they give you the solubility, you're going to have to convert that into the molar solubility, so you can calculate how many cations and anions are present here, and then calculate KSP. Now, in the same way, if you were given the KSP, you should be able to work your way backwards to calculate the solubility of the compound, all right? Now, if you have two compounds, you cannot always predict whether one of them is going to be more soluble than the other one based on the value of KSP. Because remember that we looked at some examples where some compounds generate, let's say, 2 or 3 units of a particular ion. Other ones generate different numbers. And so KSP by itself is not going to be sufficient for us to determine whether one compound is more soluble than another one. That is where the solubility or the molar solubility comes in, all right? Okay, so let's do a practice problem here. What is the solubility of silver chloride in grams per liter if the KSP is 1.8 times 10 to the negative 10? Don't forget, sometimes in your homework assignments and stuff, they will give you the KSP value. Sometimes you're going to have to look it up, all right? Just be aware of that. So in this case, we gave it to you. Okay, ready? So just like any other equilibrium problem, what do? Write out the equation, in this case for the solubility of silver chloride. And we're going to do, of course, ice. That's right. We're going to do an ice table here. So remember that in equilibrium, the undissolved solid is not going to play a role in here. So when you first form a solution, let's pretend you're putting the silver chloride in and you have no silver ions and no chloride ions. Now, remember, in this case, there's a change that's going to happen. The change is essentially how many moles per liter of solid are going to actually dissolve. And since each mole per liter of solid that dissolves generates 1 unit of silver and 1 unit of chloride, in these solubility equilibria, instead of X or Y or whatever, we're going to use the molar solubility as our variable, all right? So you're going to be generating S moles per liter of silver ions and S moles per liter of chloride, because that is how many moles per liter of compound will dissolve, all right? And so at equilibrium, what we have is we have S moles per liter of silver ions, S moles per liter of chloride ions. So what we're going to do then is we are going to find out what is the value of S, right? So since KSP is the product of the two molarities, and we just found that that molarity is S, so this would be S squared. But we don't know what S is. We're trying to find out what it is. So S is going to be the square root of the KSP, square root of 1.8 times 10 to the negative 10. It's 1.3 times 10 to the negative 5. Okay, that number represents the molar solubility of this compound. These are the number of moles per liter of silver chloride that will actually be dissolved. But of course, when it dissolves, it dissociates. So you have, S moles per liter of silver ions, S moles per liter of chloride ions. So let's write down those concentrations here, right? That's 1.3 times 10 to the negative 5 for silver and for chloride. Now, the question was, what is the solubility? In the absence of any other specifics, assume that solubility means the grams per liter, all right? Unless they ask you for something more specific than that. So default to grams per liter. Okay, so we have moles per liter here, right? So you know how to convert that, right? That means you have 1.3 times 10 to the negative 5 moles of compound dissolved per solution per liter. And we need grams, so we're going to multiply out times the molar mass of silver chloride, which is 143.35 grams per mole. Again, moles cancel out, and your final result shows you 1.9 times 10 to the negative 3 grams per liter, or you could also say 1.9 milligrams per liter is actually what is dissolved. So a saturated solution of silver chloride should have 1.9 milligrams of compound dissolved per liter. All right? Let me know if there's any questions. And we're going to do a little problem solving of our own. Let me give you a few seconds to write that down. So I think hopefully you have this in your handout. But if not, just write it down. Oops, sorry. I keep hitting the wrong keys here. The solubility of lead 2 chromate is 4.5 times 10 to the negative 5 grams per liter. What is the KSP? Okay, hopefully, I don't know if you have this in your handouts. If not, please write it down. But in any case, I'm going to come back here to our, oops, where is my, all right, here we go. So here we have our same problem. Let me zoom in a little bit if I can. A little more. Here we go. All right. So what is KSP? So again, they give you the solubility. So we need to find S, molar solubility. So that we can then calculate KSP. All right. So obviously, first thing we're going to do is we're going to have to convert the solubility in grams per liter into the molar solubility. So we need here the, I'm going to need the molar mass of this compound, lead 2 chromate. And if you forgot what that is, just go ahead and look it up. This is not Chem 1A. I'm not quizzing you or testing you on whether you know how to write these formulas. This was Chem 1A stuff, but if you forgot how to do it, just look it up. Okay, So I believe that is something along the lines of 323.20 grams per mole. And so that means that S, the molar solubility, would be 4.5 times 10 to the minus 5 grams per liter. And you have over here that 1 mole is 323.20 grams. So those cancel out. And so we have, you can solve that. You're going to get to 2 sig figs here, 1.4 times 10 to the minus 7 moles per liter. All right, that's S. So let's go ahead and write out the equation. It helps for us to keep track of things. So this is the compound lead chromate. And we said that in water, it would dissociate, whatever portion of it dissolves into lead and chromate ions. And again, we can do a mini ice table here. For however moles per liter of lead chromate dissolve, you're going to form S moles per liter of each ion, which means that at equilibrium or at saturation, you would have S moles per liter. All right. Now, in this case, KSP would be the product of the concentrations of each ion. But since each one is S, this would be S squared. We already found out what S was. 1.47, I'm sorry, 1.4 times 10 to the minus 7. And don't forget, KSP, much like other equilibrium constants, does not require us to put units in it. Let me get this out of here. All right, there we go. Squared. And, once you do your rounding and stuff, this should come up to something like 2.0 times 10 to the minus 14. Once you round up. I mean, if you came up with 1.9, I think that's fine. I'm sorry, I don't have my calculator with me right now, so I can't check it for you, but it's somewhere in that range. It depends on how you round things. And again, also, if you kept this number here without rounding, and then you put it in here, you squared it right away, you might get a different thing. But I think one thing you've noticed by now is that when we deal with these equilibrium constants of both Ka, Kb, and now KSP, you realize that you rarely ever go beyond 2 sig figs anyway, because you can see this is a very small number. So to fuzz over was this 2.0 or 1.9, not a huge, not a huge concern, to be honest. Okay. Okay, let's go back to our PowerPoint here and see where we're at. Okay, here we go. Okay, so we have the answer to that one. And here is a table that shows you some relationships. And I think it's important. I think right now we have dealt with some fairly, kind of simple cases where you have, like a 1-to-1 ratio of the two ions, right? Where the KSP is simply the molarity of one times the molarity of the other one. But you're going to encounter other situations that are listed here, like silver carbonate, let's say lead fluoride, aluminum hydroxide, calcium phosphate, all these guys, where the actual dissociation of these guys involves these stoichiometric coefficients here, all right? And so when you calculate the actual KSP, you had to take into account, for example, in the case of silver carbonate, right? In this case, that your expression is going to be 2s squared times s. In other words, 4s cubed. And so if you solve that for s, then you're going to have to take a cubic root of those things. So hopefully you guys know how to do that in your calculators. Although we're not going to have a lot of those kind of problems. I tend to keep things a little simple. All right, cool. So what we've done right now is we have done a little survey of these KSPs. All right. And what I'd like to do now is I'd like to come back here and see if anybody has any questions about what we've done so far. Any questions? You can either put it in the chat room or you can raise your hand or unmute your mic and ask. We're good? Okay, I'm gonna do something here that I haven't done before, and that is that I'm gonna essentially